Good evening, dear students. In last class, we discussed about the sodium and potassium system. Phase diagram of sodium and potassium system. Okay, in today's class, I am going to discuss about the Clausius-Clapeyron equation. This is very important for the 5 marks question. 5 to 6 marks. Okay. Clapeyron or Clausius-Clapeyron equation. Clausius-Clapeyron Clausius-Clapeyron equation. Here the Clausius-Clapeyron equation. The Clausius-Clapeyron equation is used to estimate the vapor pressure of pure solids or liquids. Here the estimation of pure solids or liquids. If you are using in water molecule, water system, sulfur system, using this Clausius-Clapeyron equation. Here, one system is in equilibrium. Solid or liquid. This is the solid, and this is going to equilibrium with liquid, or liquid which is equilibrium with vapor, or here solid which is equilibrium with vapor, or vapor equilibrium with solid. Here this is known as the melting or fusion, and this is known as the vaporization. And this solid to vapor, this vapor to solid. If you converting solid to liquid, or liquid to solid, or liquid to vapor, vapor to liquid, yes, solid to vapor, vapor to solid. This is known as sublimation. This is known as the sublimation here. These are the equilibrium. These two are equilibrium, and any of these phases, it is meet at one point. That's why it is known as the equilibrium. And equilibrium, it tells the free energy, the change in free energy. That gives free energy according to the thermodynamic. The equation is that is delta G is equals to 0. For it is here accompanying the process is 0, because of here at equilibrium state, here it gives free energy, change in gives free energy here, delta G is equals to 0. This is at equilibrium state for a system in equilibrium. For a system in a equilibrium, that is this free energy and this free energy, delta G is equals to 0. This equation number is 1. Here this is the equation number 1. I write only equations and number, explanation I did it. equation number 1, change in free energy gives free energy delta G is equals to 0. This is equation number 1 for equilibrium. The system is in equilibrium. Here the further this variation of temperature and pressure here. The variation of free energy with temperature and pressure is given by the total differential equation. Here the total differential equation according to thermodynamics, that is the gives free energy differential equation for the gives free energy. Here this is a differential equation. dg is equals to VdP minus S dt. This is a equation number. Here these are the differential of gives free energy with temperature and pressure. The volume, this is here. Here V is a volume, molar volume. Here S is a entropy. This change in temperature. Here differential pressure. This is a temperature. Here this is a equation number 2. This is a equation number. Here, I told already, this is the equilibrium state. Equilibrium state, this is a solid, and another, this is a liquid, this is a liquid. I give an example. Here, I take the system, I consider a system consisting of two phases. Phase first and phase 2, equilibrium at temperature T and pressure P. Here, see here. This is a system consisting of two phases. The system consisting of two phases. Here, this is a phase first and this is a phase second with temperature and pressure. Here P is the temperature and P is the pressure. Here this is a gives energy G1 and this is a G2. Or you can 1 and 2 here. Take this number. 1 and 2. This is the system. It consists of four. You consider a system. It consists here the solid, here the liquid. Here these two are at equilibrium state. These two are at equilibrium state. That is delta G is equals to here 0. You know here the delta G is equals to 0. Here under these two, it contains two phases. One is a G1 and another is a G2. And under this condition, suppose the energy of phase first is a G1 and another it corresponding to energy of second phase is a G2. If temperature of the system is changed from T to T plus here. This temperature changes T plus and pressure changes P to T plus. According to this system, constitutes two phases, first phase, second phase, and if suppose it gives energy changes, this is the G1 first phase and corresponding to that of this is the G2 and the conditions change in temperature and pressure from T to T plus T to T plus D. Suppose the corresponding change in gives free energy. Phase first is G1. This corresponding free energy it is changing here. I write here. Phase first is at equilibrium state here. Right. is the system and two phases. This is a phase first and this is a phase second. It is changing in equilibrium. These two phases are equilibrium and it changes. First phase is G1, D2 and it gives energy G1 to differential plus D0. This G1 plus D and this G2 plus D. This is the equilibrium state for phase first and phase second. This is the diagram for the phase equilibrium at temperature and pressure. This diagram is the phase equilibrium. The phase equilibrium of temperature and pressure. It changes and at the T plus Dt and another T plus D. T plus D. This system. It is equilibrium with formation here. The phase versus G1 plus D1 equals to equation G2 plus G2. Here these are the diagrams. Next, here you taken dV is equals to V dV minus S dt, equation number 2 here. According to equation number 2, right here according to this system, dV G1 here, according to the second equation, and this equilibrium state you can write here. This equation you change here. dG1 is equals to this dG1 is equals to V1 dV minus S1 dt, and second equation, another equation dG2, this second phase dG2 is equals to V2 dV minus S2 dt. Right here equations. Remember this diagram. Only it's changing the equilibrium. Phase 1 to phase 2, it gives free energy and it changes to G1 plus G2. Here, according to equation number, this equation above equation here dG1 this one dG1 is equals to this V1 dV minus S1 dt. This is equation number. Next, second phase. This is the first phase. Second phase dG2 is equals to V2 dt minus S2 dt. This is equation number. This equation is equation, and here where V1 and S1, here the V1 and S1 are the molar volume and entropy of phase first, and it is second one here V2 and S2 molar volume, here the molar volume and the entropy of phase 2. This is molar volume and entropy. This is a phase first and molar volume and entropy. This is a phase second. Here corresponding value for phase 2. Next, that is consider here we know that the phase first is in equilibrium with phase 2. This is the system. You consider this is the phase first and this is the phase 2, and these two phases are at equilibrium. You know the equation. This delta G is equals to 0 here. Delta G is equals to 0. This is the, you can write the in this changing, and here these two are equilibrium, and it is the solid is going, these are the water molecule here, the changing here, the transforming here, the vapor molecules, and these are coming here, these are going to here, the state first and phase 2, this equilibrium state, and here you can write the gives state, the gives energy here, we write G2 minus G. G2 minus G is equals to G. See here, this is the G2 minus, as in thermodynamics you are also written the product minus reactant. Here also the final value and initial value. G2 minus G1 is equals to 0 here. This is already known, this delta is equals to 0, and in place of this G2 minus G1, so add this here D G1 minus this D, sorry, dG2 minus dG1 is equals to 0. Next, we have to write this dG2 is on side dG1. This is the equation number 1. This equation number is 5. Okay, here this is this value, this dG2 is equal to dG1. Substitute this equation, the value for this dG1, the value is d1 dt minus s1 dt, and v2 dt minus s2 dt. The third equation values substitute in the fifth equation here. I substitute here, substitute equation third and fifth. Here substitute equation third and fifth. Here dG2. dG2 means this one. V2 D2. I substituted here dG2 value V2 dP, V2 dP minus S2 D2 is equals to this one, is dG1 V1 dP minus S1 dP. Okay, here S1 dP. Next, write this one V2 dP and this one V1 dP. This common, this V2 minus V1, I take a common here, the V2 minus V1. V2, this comes this side, this is negative V2 minus V1, and common is D. Next is equals to, this goes to here S2 minus S1. S2 minus S1 dt. Next, S2 minus S1 dt, and next, and you write V2 minus V1, change it. This is the delta V dP is equals to this changing, it will be delta S heat. delta S into this one here dp by dt. We can take this rearrange this equation. This one dp is divided by dt is equals to delta S divided by delta S divided by delta V. This is the equation number 6. This is the equation number 6. Here the dp dt delta S and delta V. Delta S is the change in entropy. Here the delta V is taken as V2 minus V1. It is the molar volume change. This is the molar volume change delta V, and the delta S is S2 minus S1 is the molar entropy change. Here delta V is the molar volume change and delta S is molar entropy change. Molar volume change and molar entropy change. And next, here the phase first changes to phase second, and if this occurs here according to this equation, at the temperature T is a melting point or a boiling point. Here the temperature T is a melting point or boiling point, and here the temperature, melting point and boiling point, you will take a heat, latent heat, that is a delta H is a latent heat of transformation. Then the equation 6, then it is rearranged, it is substitute with the latent heat. Here the latent heat of transformation, that is delta H, where delta S is equals to latent heat delta S is equals to delta H divided by T. This is the equation. Next, and this value put in this equation. Here, see dp divided by dt is equals to dp divided by dt is equals to delta S means delta H by T. Here delta S, I am adding delta H. Here substituting delta H divided by T into delta V. T into delta V. T into delta. See, the only substituting the delta S value according to thermodynamics, the delta H divided by T. This value substituted in equation number 6. Here dp divided by dt is equals to, in place of you are substituting, you are putting the value of this delta S value. Delta S is a delta H divided by T, and this same value, this is a delta V. This is the equation number 7. This is the equation number 7. This equation number 7, and this equation is known as Clapeyron equation. According to this equation is known as a Clapeyron equation only. And afterwards, find out the Clausius. First, this equation is known as a Clapeyron equation. This equation was first derived by Clapeyron in 1934. Clapeyron in 1934. That is, equation is known as a Clapeyron equation. This equation is this one, Clapeyron equation. this Clapeyron equation. Up to here, equation number 6. This is the equation number 7. Application of this Clapeyron equation. This is the application of Clapeyron equation. Or you can take the application of Clapeyron equation. dP is that solid to liquid. Here it is various physical between the melting point and vaporization of and sublimating for the for melting equilibrium. That is for melting equilibrium, that is solid to liquid. This is very important for 5 to 6 marks question. Application of Clapeyron equation. Applications here for the melting equilibrium. For the melting equilibrium that is solid equilibrium with liquid. Taken this one, solid equilibrium with liquid. Here the final equation is dT by dt is equals to delta H divided by T into delta V, and here the delta H, this is a melting. This is known as a melting here. Okay, you consider here delta H is equals to delta H here, because here melting takes place and latent heat of melting. This is the latent heat of melting. This delta Hm, and the T is taken as Tm. T is taken as Tm. Here temperature of this is the melting point. This is the melting point. The equation is that equation 7 may be written as here according to this. Why this is replace delta H, replace delta H, and that is here dP by dt is equals to dP divided by dt is equals to delta H replaces delta H, and divided by T is replaces T into delta, and this is known as the equation number. This is the equation number 3. Here delta V is equals to, delta V is equals to V2 minus V. Sorry, V1 minus, or you can take delta V is equals to, that is the V2 minus V1. Here you can take this is solid to liquid. Here delta V is equals to VL. Here delta V is equals to VL, this one, liquid. VL minus of solid VS. To take from this, first is final and finishing. Here, delta V is equals to VL minus VS. This is solid to final, VL minus finishing VS. The VS is the more dP divided by dP is equals to delta Hm divided by Tm. In place of delta V, you can write VL minus V. This is, I realize this one, dP divided by T. Change this one, dt divided by T. This one changes dp by dt, and this is upper and this is numerator and this is the denominator. Here also changes. This is Pm Vl minus V. Pm Vl minus Vs divided by delta H. This is the equation number 9. This equation number is 9. After equation number 7, that is known as the Clapeyron equation. It is called in 1934. Clapeyron is scientific derived Clapeyron equation. Afterwards, it is the application of Clapeyron equation for the melting of equilibrium. I take an form of solid to liquid, it is equilibrium. And here the latent heat of transformation, I take a delta H is equal to delta HM and here the melting heat there, the T taken as a temperature, the melting temperature or melting point, here dTm, and replaces the delta H in place of delta Hm, and here dP in place of Tm, and dP by dt is equal to delta Hm divided by Tm delta V, where delta V is taken as a Vl minus Vs, and if this replaces this delta V value Vl minus Vs, dP divided by dt is equal to delta Hm divided by Tm Vl minus Vs, and here it is rearranging this equation dP divided by dP is equal to Tm Vl minus Vs divided by delta Hm, and this is the equation number 9. This equation gives the melting point with pressure. This gives the melting point with temperature. This equation gives the melting point with pressure. The liquid, the equilibrium state is liquid. I taken first is a solid to liquid. Next, I take here the liquid to vapor. Liquid to vapor. I write here. I change this one. Replace in place of solid to liquid. The liquid. Second one is liquid to vapor using that equation. I use this equation. Here for the vaporization, I take a for vaporization. First one is a for melting, second one is a for vaporization. For vaporization, liquid to equilibrium vapor. Here you replace it the Clapeyron equation, equation 7 here. The equation 7 is next form equation number 8. The equation number 8 here the dP by dt. Right, equation number 8 dP by dt is equals to delta H. I write that here the delta H divided by TB or Tm here the TB. Initially, just it is understood the TB Vs here. This is a liquid and this is a vapor. You finally write here Vv minus Vl. Vv minus Vl. This is the Vl. In first solid to liquid, I taken this is the delta V is equals to that is the Vl minus Vs. Here the V minus this V minus Vl taken liquid. Here dP by dt is equals to delta H divided by V into V minus Vl and here the VL is the this VL is the molar volume and this V is the molar vaporization or molar volume of vaporization. V means volume. Yeah, V here, this small V here, the vaporization it is the molar volume of liquid and this is the molar volume of vapor. And here the volume of the liquid very small as compared to the vapor. Here the very small as compared to this one. The equation number is 10. This is the equation number 10. It is written as this is compared to this is very small as it will be is very small as compared to the volume of the vapor. Here the equation number 10 may be written as dp by dt is equal to this is neglected as compared to this one is very small and here this one is neglected. We have written the t b into v. This is also neglected here. I write the equation here dp by dt is equals to delta h divided by P into V into this is the V into and here further we have to assume after this equation this is the equation number 11. This is the equation number 11 and then it is further assuming the vapor behave like an ideal gas. You know ideal gas equation that is the PV is equals to nRT clearly is an integer that is PV is equals to RT clearly. P is equals to or V means the volume is taken here. Here the PV is equals to and this one PV is equals to RT divided by and this is the equation number 12. This is equation number 12. This is the equation number 12. That is the dV is equals to RT by P. This value is substituted in this equation. That is the equation number 12. What happens here? That is dP by dP is equals to you substitute dP by dt is equals to delta H T Vv means RT by P. We go upside that is the delta H into P. RT means this is the T square. I write here substitute this equation. Okay, here dP divided by dt is equals to delta. This is the delta H divided by T. Okay. V means here RT by T. RT by T. Here RT equals to T is multiplication and here T is the square. You take T into T square and another is a half. Here dP by dt is equals to delta H divided by RT square multiplied by pressure here. You can take separate out the this T is take this side here. Here 1 by P into dP divided by dt is equals to delta H divided by RT square. This is delta HV. This is the HV that is a vaporization. Delta HV divided by RT square. This is the equation number 30. This is equation number 30. Next, 1 by P dt by dt is equals to delta HV divided by RT square. This equation is known as the 9th equation or 13th equation. You cannot do this equation. Next it is here this one. derivative of this equation, you can take d of ln of here t. I taken d of ln of t divided by this one divided by dt is equals to delta hv or t square and this equation is 30. Equation number is, or you can give this equation number is 13, this is equation number 14. As well as here, the d of ln of p divided, this is a derived form of this dt by dt. Here, the d of ln of p divided by dt is equals to delta hv divided by rt square. This equation is a 30. Equation number is a 30. And this equation is known as a, this equation is called as a Clausius-Clapeyron equation. Here Clausius-Clapeyron equation, and it is was derived by Clausius during the details of this Clapeyron equation, and give the finally this equation is a Clausius-Clapeyron equation. This is a Clausius-Clapeyron equation. Next, this equation, the 13 equation is very commonly it is written by in the form of, it is called as a integrated form of Clausius-Clapeyron equation, and it is may be derived, it is modified, the integrated form of Clausius-Clapeyron equation. Then it is continued, this equation is modified, taken log ln here. This is continuation, this is the Clausius equation, this is the Clapeyron equation. Here this is a modified integrated Clausius-Clapeyron equation. In your examination, you have to write up to here only for a class, derive an expression for the Clausius-Clapeyron equation up to here. But integrated Clausius-Clapeyron equation, you modify this equation here. I taken d ln of p, d ln of p is equals to delta hv divided by rt, d ln of p divided by dt, or you can take this is a here this d ln of p is equals to delta h v divided by rt square multiplied by this dt. And here the limit you take an integration form, and temperature here changes T1 to T2. The integration form T1 to limits is T1 to T2 and pressure P1 to P2. Here take P1 and P2. First it is adding first upper limit and lower limit. Here the upper limit, first lower limit is P1, upper limit is P2. You integrate this equation, that is the equation number. Here this is the 13 equation number, and this is the 14 equation number 14. This is the equation number 14, and integrating this equation. Here the integration, this is the pressure, here P1 to P2, this is the P1 and this P2, here d of ln of is equals to integration of T1 to T2, here delta hv divided by rt square dt. This is a common outside here, delta hv divided by applying the limits here, the ln of here this is the ln of p and limit is p1 p4 is equals to you can take outside delta h divided by r this one delta h b divided by r and this is the relation of this 1 divided by this minus here this is 1 divided by r so r is taken outside here 1 by t 1 by t delta h br is outside here minus 1 by dt here t1 to t2 limit is t1 t2 here applying limits here first is the upper limit minus lower limit here ln of P2 minus ln of P1. Here this is applied here and next it is take minus delta HE divided by R and apply here the limits 1 by T2 minus there minus is taken outside 1 by T2 minus 1 by T1 minus 1 divided by T2. This is of applying the limits and finally here the equation gets land. You can write also this is when it in subtraction you write division and division write subtraction. This is the rule of logarithms here ln of p2 minus ln of p1. I can write here ln of p2 divided by p1 and is equals to this one. I take here the minus is a common and 1 by t1 minus 1 by t2 divided by r here 1 by t1 minus 1 by t2 1 divided by t2. Here next we can take the logarithmic form here the 2.303 is the value this value is used in chemical kinetics also here this is ln of p2 by p1 is equals to delta hp by r into 1 by t1 minus 1 by t2 the minus is cancelled here taken minus is outside the minus is here 1 by t1 minus 1 by t2 and the finally the changing the natural logarithm here is changing natural changing natural logarithm we are changing natural logarithm to the logarithm to base 10 logarithm to logarithm base 10 here and here this is the ln of p2 by ln of p2 by p1 I am taking logarithm here 2.303 log base 10 p2 by p1 and this equation is 2.3 log of base 10 log base 10 this is p2 divided by p1 is equals to here the delta h delta R is 1, delta H B delta R, and here 1 by T1 minus 1 by T2. You take one, this one delta H will be there, and you take a common here, this is the T1 and T2 is common, and T2 minus T1. Here, numerator is here, T1 is taken here, and this is the T2 minus T2. This is the right, and next one is final equation. The integrated Clausius-Clapeyron equation. This is the final equation. This equation is the equation number 50. This 2.303 log base 10 here. The log base 10 here, this comes to numerator here. Log base 10 P2 divided by P1 is equals to delta H B divided by 2.303 R 2.303 R into T2 minus T1 divided by T1 into T2. This is the equation number 50. This equation is called as a integrated form of Clausius-Clapeyron equation. This equation is called integrated form of Clausius-Clapeyron equation. This is very important, this equation. This is the integrated form of Clausius-Clapeyron equation. And here some application of Clausius-Clapeyron equation. I am only detecting here. First one is if the vapor pressure of liquid is known, any of the liquid vapor pressure is known, and at one particular temperature, the value of any other temperature can be calculated. You know the vapor pressure of the liquid and the particular temperature, you can find any of the other temperature can be calculated. And if the latent heat of vaporization of the liquid is known, latent heat of any of the other liquid is given here, or it is a known. This is the first application. Second application, if the vapor pressure of liquid at two different temperature are known. Here the vapor pressure of two different temperature is known. The latent heat of vaporization of the liquid can be calculated. This is the second application. And third one, if the boiling point of a liquid is known, and at some particular pressure, the particular temperature, you will find in the temperature, any other temperature. You are here the third application, if the boiling point of the pressure known, some particular pressure, the boiling point of any other pressure can be calculated, and provided the latent heat of vaporization of the liquid is known. And the fourth application, the one of the use of this integrated Clapeyron-Clausius equation is determined for phase transition will occur in a given situation. These are the four applications. For example, how to calculate how much pressure is needed to melt ice at a temperature below 0 degrees Celsius. This is the question here. Arise here the Clausius-Clapeyron equation. This is a very important for 4 to 6 months question. When in examination derive an expression for Clausius-Clapeyron equation. You don't write up to here. In your examination, only write the equation number, it is derived the expression for integrated form of Clausius-Clapeyron equation. You write up, you derive the equation up to this equation number 50. You know here one note here. The dp by dt delta h is fusion here. Delta here VL minus Vs initial final and initial concentration here. Here is the the water is anomalous behavior of water here. The water is in liquid, the volume is decreases. When water is in liquid, the volume is decreases. When water is in ice, the volume is increases. This is the anomalous behavior of water. Here the ice, the V of ice, the volume of ice is greater than volume of liquid. Here the volume of ice is greater than volume of liquid. Therefore, here comes the dp by dt at equilibrium is 0 degree Celsius to 4 degree Celsius. This is the expansion in condition here. That is a dp by dt value is equals to, that is according to this ice and liquid, the dp by dt value is negative. dp by dt is equals to negative, and this comes to 0. It is in the equilibrium state. And here this is a melting state, that is a fusion, that is solid to liquid. Here dp by dt is equals to negative when it is a melting takes place, that is solid to liquid. In equilibrium solid to liquid, dp by dt value is equals to negative. This comes under in a one component system, that is the water system. And another note here, when liquid to vapor. The liquid to vapor, the Clausius-Clapeyron equation, ln of P2 by P1, it is a ln of P2 by P1, you can take here delta H by R T2 minus T1 divided by T1 T2. The second condition, you take liquid to vapor, this is at equilibrium, this liquid to vapor at equilibrium, this dp by dt is equals to delta H vaporization divided by T into this, that one here, this T into delta V means here gas minus liquid. In gases minus liquid, here as compared to the gas and liquid, here the vapor is here, the liquid is as compared to as small, it is present here as compared to the vapor. Here the liquid is neglected here. Then the delta of the volume of the molar volume of the vapor is given. It is the value is comes under this equilibrium state, liquid to vapor. The dp by dt value is positive. This dp by this value dt is equals to positive. This comes the positive. This is a very important for any the competitive examination. This one. I hope understood this derivation, the Clausius-Clapeyron equation, and the integrated form of Clausius-Clapeyron equation.